There is a plant that doesn't need soil. It makes its own fertilizer from the air. It grows on water, and it produces more protein per acre than soybeans, more than eggs, more than almost any crop humans have ever cultivated. Millions of years ago, this single species spread across an entire ocean, pulling so much carbon from the atmosphere that it helped cool the planet. It didn't just grow. It changed the climate of Earth. For centuries, farmers across Asia treated it as something sacred. They built traditions around it, protected it, passed down the knowledge of how to grow it from one generation to the next. And today, in parts of the modern world, it's classified as a pest, a noxious weed, something to control, something to eliminate. In the United States, transporting certain species of this plant across state lines is restricted by federal regulation. The same organism that once helped feed civilizations is now treated as a threat. So what changed? Was it the science, or was it something else? Because in the 20th century, another discovery reshaped agriculture, one that turned nitrogen into a global industry. And suddenly, a plant that could create its own fertilizer was no longer just useful. It was inconvenient. This is the story of Azolla, a plant that grows without soil, feeds from the air, and may have been forgotten, for reasons we're only beginning to understand. At first glance, it doesn't look like much, just a thin layer of green floating on still water, like moss or algae, or something you'd barely notice in a quiet pond. But look closer. Each tiny piece is a plant no larger than a grain of rice, with delicate overlapping leaves forming dense floating mats. This is Azolla, often called the mosquito fern. And inside every leaf, something extraordinary is happening. Living within Azolla is a microscopic partner, Anabaena azolae. This isn't a temporary relationship. It's one of the oldest and most stable symbioses in the plant kingdom. For over 100 million years, these two organisms have evolved together so completely that neither can survive without the other. But what makes this partnership unique isn't just its age, it's what they do together. While most plants depend on nitrogen from the soil, Azolla doesn't. Its internal cyanobacteria can capture nitrogen directly from the atmosphere and convert it into a form the plant can use. In other words, Azolla doesn't wait for fertilizer. It makes its own. No soil required, no synthetic inputs, just water, sunlight, and air. Even more unusual, this relationship is passed down from one generation to the next. When Azolla reproduces, it carries its bacterial partner with it, ensuring that every new plant is born with the same ability. This is not a plant supported by its environment. It is a self-contained biological system, a floating ecosystem complete in itself. And once you understand that, the rest of the story begins to make a lot more sense. Once you understand how Azolla works, the next question is simple. How effective is it? The answer is difficult to ignore. Most nitrogen-fixing crops like soybeans are already considered powerful in agriculture. On average, they can fix around 400 kilograms of nitrogen per hectare per year. That's one of the reasons soy became so widely adopted. But Azolla operates on an entirely different scale. Under optimal conditions, it can fix up to 1,100 kilograms of nitrogen per hectare per year, nearly 3 times more than soybeans. And that's just the beginning. Its protein content ranges from 19 to 30% of dry weight. For comparison, whole eggs contain about 13% protein. Soybeans reach around 36%, but require fertile soil irrigation and a full growing season. Azolla doesn't. It grows on water. It requires no traditional farmland, and it doesn't follow the same timeline as most crops. Because Azolla doesn't grow slowly, it multiplies. Under the right conditions, its biomass can double every 2 to 3 days. That means a small surface area can quickly turn into a dense, harvestable layer in a matter of days, not months. When researchers modeled its output, the results were striking. Up to 9 tons of protein per hectare per year. No other food-producing system comes close at that scale with such minimal inputs. No fertilizer, no soil, no complex infrastructure, just water, sunlight, and a biological system that builds itself. Of course, real-world conditions vary. Temperature, water quality, and management all affect performance. But even when scaled down, the pattern remains high efficiency, rapid growth, minimal input. And that raises a deeper question. If something this productive has existed for centuries, why isn't it a central part of modern agriculture? Long before modern science began measuring nitrogen levels and protein yields, farmers had already discovered something remarkable. They just didn't describe it in scientific terms. They described it through results. Travel back to 6th century China. A scholar named Jia Sixi was compiling one of the most important agricultural texts of his time, the Qimen Yaoshu, or Essential Techniques for the Welfare of the People. Among hundreds of farming methods, one practice stood out. Rice farmers were growing a floating plant alongside their paddies. When they incorporated this plant into the soil, something changed. Yields increased consistently. No additional fertilizer required. This wasn't a new discovery even then. It was already an established technique passed down through generations. Now move south to Vietnam. Here, Azolla wasn't just used, it was respected. In some villages, farmers built small temples dedicated to the plant. They held annual festivals celebrating its harvest. It wasn't seen as a tool, it was seen as something worth honoring. Knowledge of how to cultivate it, especially how to preserve it through extreme heat, was guarded carefully. Only certain families knew the full method, and they passed it down like inheritance. Farmers from other regions would travel long distances just to obtain small starter cultures, because without it, their yields suffered. By 1973, this knowledge had scaled. In northern Vietnam alone, over 500,000 hectares of rice paddies were using Azolla as a natural fertilizer, and the results were measurable. Rice yields increased by 20% or more without synthetic inputs. This wasn't experimental, it was proven, it was practiced. And for centuries it worked, which makes what happened next even harder to explain. Up to this point, Azolla might sound like an efficient fertilizer, but it's more than that. It's also food. In recent years, researchers have taken a closer look at its nutritional profile, and what they found closely matches what traditional farmers have known for generations. Studies from institutions like Penn State University have shown that Azolla contains significant levels of protein, with digestibility rates around 78%. That means the body can actually use most of what it consumes. But protein is only part of the picture. Azolla also contains vitamin A, vitamin B, 12 beta-carotene, iron, calcium, magnesium, essential amino acids. In some cases, these nutrients appear in proportions comparable or even superior to common plant-based foods like soy. And unlike many crops, Azolla doesn't require fertile soil irrigation systems or long growing cycles. It grows on water, it regenerates rapidly, and it can be harvested continuously. In terms of preparation, it's surprisingly versatile. Fresh Azolla can be added to salads. Cooked, it behaves similarly to leafy greens like spinach. Dried and processed, it can be ground into flour and incorporated into other foods. Taste descriptions vary, but many researchers describe it as mild neutral and easy to combine with other ingredients. Of course, like any food source, proper preparation and sourcing matter, but the implication is difficult to ignore. This isn't just a plant that improves soil, it's a potentially complete renewable food system growing quietly on the surface of water with almost no external input. and yet it remains largely unknown. Now step far beyond human history, back 49 million years. During the Middle Eocene, Earth looked nothing like it does today. The Arctic wasn't frozen, it was warm. Palm trees lined the coasts. Crocodiles swam in open waters near the poles. Global temperatures were significantly higher, and atmospheric carbon dioxide had reached extreme levels estimated at around 3,500 parts per million. The planet was locked in a greenhouse state. Then something unusual happened. Due to continental drift, the Arctic Ocean became almost completely enclosed by land. Fresh water from rivers began to accumulate on the surface, forming a thin, stable layer above the saltwater below. And that created the perfect environment for one organism, Azolla. Once it appeared, it spread rapidly. Imagine an entire ocean, millions of square kilometers, slowly turning green. Floating mats of Azolla covered the surface, expanding day by day. But what made this event extraordinary wasn't just the growth, it was what happened next. As Azolla grew, it absorbed carbon dioxide from the atmosphere through photosynthesis. When it died, it sank to the bottom of the ocean, where low oxygen conditions prevented it from decomposing. That carbon didn't return to the atmosphere, it stayed trapped. This cycle repeated for hundreds of thousands of years. Evidence for this event was confirmed in 2004 during the Arctic coring expedition, when scientists drilled deep into the Arctic seabed. What they found were thick layers, meters deep of fossilized Azolla remains, a continuous record of massive biological activity. And the atmospheric impact was profound. Carbon dioxide levels dropped from around 3,500 parts per million to roughly 650 parts per million, an estimated 80% reduction. Global temperatures began to fall. Polar ice started to form. The Earth shifted from a greenhouse state toward an ice age, all triggered in part by a single floating plant. Today we talk about climate solutions in terms of technology, infrastructure, and large-scale intervention. But 49 million years ago, one of the most powerful climate shifts in Earth's history may have been driven by something far simpler. A plant, floating on water, quietly changing the atmosphere. Today, atmospheric carbon dioxide sits at around 420 parts per million and continues to rise. It's far lower than during the Eocene, but it's increasing faster than at any point in modern human history, which brings us back to a familiar question. If a plant once helped reduce carbon on a planetary scale, could it play a role again? Researchers are beginning to explore that possibility. Studies suggest that a single hectare of Azolla cultivation can capture over 20,000 kilograms of carbon dioxide per year under optimal conditions. That's not a global solution on its own, but it's not insignificant either. Organizations like the Climate Foundation and multiple university research groups are investigating how Azolla might be used in controlled systems, from carbon capture ponds to integrated agricultural models. The idea isn't to recreate the Arctic event. That would be unrealistic. But to understand the mechanism and apply it at a human scale, because Azolla offers something unusual. A natural system that simultaneously captures, carbon, produces biomass, generates usable nutrients, all without requiring industrial infrastructure. Of course, there are limitations. Water availability, ecosystem balance, and scalability all present real challenges. But the fact remains, this is not a new idea. It's a rediscovered one. And as the search for sustainable solutions accelerates, some of the most promising answers may not come from what we invent, but from what we choose to remember. In 1909, two German chemists, Fritz Haber and Karl Bosch, developed a method that would reshape global agriculture. It's known as the Haber-Bosch process. For the first time in history, nitrogen could be taken from the air and converted into ammonia on an industrial scale. This was a breakthrough, and it came at a critical time. Global populations were rising, food demand was increasing, and traditional farming methods were struggling to keep up. Synthetic fertilizer changed that. It allowed farmers to boost yields quickly, predictably, and at scale. Within decades, production surged. What had once been a natural localized cycle nutrients returning to the soil became part of a global industrial system. And with that shift came something new. A dependency on inputs. Farmers no longer relied solely on natural processes. They relied on products. Each season required purchased fertilizer, external supply chains, continued investment. From a production standpoint, it worked. It fed billions of people. But it also created a massive industry now worth hundreds of billions of dollars, built around the ongoing need for chemical nutrients. Now consider where Azolla fits into that system. A plant that can fix nitrogen from the air, grow rapidly without soil, require no recurring chemical input. It doesn't integrate easily. Not because it doesn't work, but because it operates outside the model. And over time, as industrial agriculture expanded, methods that didn't align with that model received less attention, less funding, less research, less visibility. The shift wasn't necessarily about rejecting alternatives. It was about scaling what worked fastest and what fit the system best. Which raises an important point. Sometimes the most widely adopted solution isn't the only one available. Synthetic fertilizers helped increase global food production. That part is undeniable. But what happens to the nutrients that crops don't use? Because in reality, a significant portion never reaches the plant. Estimates suggest that over half of applied nitrogen fertilizer is lost, not absorbed by crops, but carried away by water, air, and soil processes. Some of it seeps into groundwater, some runs off into rivers, and some is released into the atmosphere as nitrous oxide, a greenhouse gas nearly 300 times more potent than carbon dioxide. The environmental impact doesn't stay local. It travels. Follow the Mississippi River down to the Gulf of Mexico. Every year, excess nutrients from agricultural runoff flow into the ocean, feeding massive algal blooms. At first, the water looks alive. Then it dies. As the algae decompose, they consume oxygen, creating vast areas where marine life cannot survive. These are known as dead zones. In the Gulf, this zone can exceed 17,000 square kilometers, an area larger than some countries. Fish leave. Shrimp disappear. Entire ecosystems collapse temporarily but repeatedly. And this is not an isolated case. Around the world, similar zones have been identified, some reaching tens of thousands of square kilometers. The United Nations has classified them as one of the most significant threats to marine ecosystems, all tied in part to nutrient overload. To be clear, fertilizers are not the only factor, but they are a major one. And this brings us back to a simple contrast. On one side, a system that requires constant input with measurable environmental cost. On the other, a biological system that fixes nitrogen naturally without runoff. The question isn't which one is perfect, it's whether we've fully considered the trade-offs. In modern agriculture, classification matters. The way a plant is labeled can determine whether it's cultivated or eliminated. In the United States, one of the agencies responsible for managing plant risk is the Animal and Plant Health Inspection Service. Under federal regulations, certain species are classified as noxious weeds, plants considered harmful enough to require control or restriction. Among them is Azolla pinnata, a species of mosquito fern. This classification means it is restricted or prohibited from transport across state lines without proper authorization. At first glance, that might seem contradictory. Why would a plant with such agricultural potential be regulated this way? The answer lies in ecology. Azolla grows quickly, extremely quickly. Under the right conditions, it can double its surface coverage in just a few days, forming dense mats across water bodies. These mats can block sunlight, alter oxygen levels, and disrupt aquatic ecosystems. In unmanaged environments, that becomes a real concern. So from a regulatory perspective, the classification is not arbitrary. It's based on environmental risk. But here's where the conversation becomes more complex, because the same plant that can overwhelm a pond can also fertilize crops, produce protein, and reduce chemical input when managed correctly. So the issue isn't simply whether Azolla is good or bad. It's context, control versus neglect, application versus spread. And yet the label itself, noxious weed, carries weight. It shapes perception. It influences research funding and adoption. And over time, it can determine whether something is explored further or quietly avoided, which raises a subtle but important question. How many useful solutions have been overlooked, not because they didn't work, but because of how they were classified? Azolla is not the only plant with this kind of story. If you look closely, a pattern begins to emerge. Across different regions and time periods, certain plants have followed a similar path, once valued, widely used, then gradually reclassified. Take white clover. For generations, it was intentionally included in lawn seed mixes. It enriched soil naturally by fixing nitrogen, reducing the need for fertilizer. But over time, it began to be labeled as a weed, not because it stopped working, but because lawns were redefined and chemical herbicides were introduced to remove anything that didn't fit a uniform appearance. Or consider Jerusalem artichoke, a plant capable of producing high yields with minimal input, even in poor soil conditions. Yet it never became a dominant crop. Not because it lacked productivity, but because it was difficult to standardize transport and integrate into large-scale industrial systems. These examples don't prove a coordinated effort, but they do highlight something important. Not all useful plants fit neatly into modern frameworks. Some are too unpredictable, too decentralized, too independent from external inputs. And when that happens, they tend to receive less attention, not necessarily because they fail, but because they don't align. Azolla may be one of those cases, not forgotten entirely, but pushed to the edges, where only a few continue to notice what it can do. Despite decades of decline in mainstream agriculture, Azolla never fully disappeared. It simply moved out of the spotlight. In parts of India, smallholder farmers have quietly continued using it, not because of policy, but because of results. In regions like Tamil Nadu, simple backyard systems have been developed. The method is straightforward. A shallow pit about 2 meters by 2 meters is dug and lined to hold water. A small amount of soil is added, along with organic material to support initial growth. Then a starter culture of Azolla is introduced. Within days, it begins to spread. Within 2 weeks, the surface can be fully covered. From there, it's harvested daily. Not as waste, but as feed. When mixed with traditional fodder farmers, report milk yields increasing by 15 to 20% in dairy cattle, while feed costs drop significantly. No complex inputs, no expensive infrastructure, just a system that grows itself. Similar results are emerging elsewhere, in parts of West Africa, including the Senegal River Valley field. Studies have shown that Azolla can replace a portion of synthetic nitrogen fertilizer while maintaining or even improving rice yields. For farmers, this translates into something practical: lower costs, greater independence, more stable production. And perhaps most importantly, this knowledge isn't spreading through large-scale campaigns or corporate systems. It's moving farmer to farmer, through observation, through shared experience, the same way it spread centuries ago, which suggests something important. Some ideas don't need to be rediscovered. They just need to be remembered. As interest in sustainable systems grows, Azolla is being studied in places far beyond traditional agriculture. Not just in fields, but in controlled environments, laboratories, and even space research. Organizations like NASA have explored plant systems that can support life in closed environments. The challenge is simple. How do you create a self-sustaining ecosystem with limited space, limited resources, and no external inputs? Azolla offers a compelling answer because it doesn't just grow. It performs multiple functions at once. It produces biomass, generates oxygen, fixes nitrogen, and can serve as a food source within a closed loop. In experimental systems, small areas of Azolla cultivation have been shown to support oxygen production for human needs, while simultaneously feeding fish or livestock within the same ecosystem. Projects like biosphere-style environments have already tested similar concepts using plants to recycle nutrients and maintain balance. Azolla fits naturally into this model, not as a single solution, but as part of a larger system designed around efficiency and regeneration. What makes it unique is not just what it does, but how little it requires: water, light, time, and a biological partnership refined over millions of years. From ancient rice paddies to modern laboratories to potential use beyond Earth, Azolla continues to appear in places where efficiency matters most, which raises a final possibility. The plant that once helped stabilize a changing planet might still have a role to play in the systems we build next. At this point, the facts are on the table. Azolla has been used in agriculture for over 1,000 years. It can fix nitrogen from the air. It grows, rapidly produces protein, and requires minimal input. Modern research supports many of these properties. Farmers around the world are still using it quietly, effectively. So the question is no longer, does it work? Because in many contexts, it clearly does. The real question is something else. Why isn't it more widely used? The answer isn't simple. There are valid concerns: ecological balance, scalability, control. Not every solution works everywhere. But there's also something deeper, a pattern that appears again and again. When a resource is abundant, decentralized, and difficult to monetize, it often receives less attention. Not necessarily because it fails, but because it doesn't fit. And that leaves us with a choice. We can accept the labels we've been given. What is considered useful? What is considered a problem? Or we can look closer. Test for ourselves. Observe, compare. Because sometimes the most powerful ideas aren't the ones that dominate headlines. They're the ones that quietly persist, waiting to be noticed again. So here's the question. If something could grow your food, restore your soil, and reduce your dependence on external inputs, and it was already here, would you ignore it, or would you try it for yourself?